So notebook 3 is on data structures, and the three classes of data structures that we'll talk about in this tutorial are tuples, dictionaries, and arrays. If you're not familiar with the distinctions between those, from the user perspective, I think some of the most important differences for a user, I think, between these three different data structures, and I'll go over this again later, but they are that tuples are immutable. So once you've created a tuple, you can't update it. And otherwise, tuples are ordered collections of elements. Arrays, like tuples, are ordered collections of elements. So you can look up inside of an array and say, like, what's my fifth element? The same way that you can, inside of a tuple, say, what's my fifth element or what's my first element. But an array, unlike a tuple, is mutable. So we can update an array after we've created it. We can add things to it, we can remove them, we can change out some elements for other elements. And dictionaries are like tuples in the fact that, dictionaries are unlike both tuples and arrays in the sense that they are unordered. So we can't look up the first element of a dictionary. That doesn't really have meaning. And then dictionaries are like arrays in that they are mutable, so we can update them after we've created them. And with that, let's see what it looks like to make a tuple in Julia. So we can make a tuple by enclosing our elements inside a pair of parentheses. So my first example of making a tuple is here, where we're making a tuple called My Favorite Animals, which includes the elements penguins, cats, and sugar gliders. Now, once we've created this tuple, we can index into it because tuples are ordered. So we can say, I want the first element of this tuple, My Favorite Animals. And we do that by putting the number of the element that we're interested in inside square brackets after the name of the tuple that we're interested in looking inside. One of the things you'll notice here is that the first element is penguins, which indicates that Julia is a one-indexed language. So we start in Julia counting from 1, not counting from 0, the way that you might in C or in Python, for example. And now, as I said earlier, tuples are immutable. We can't update them. So if I try to change the first element of My Favorite Animals to otters from penguins, we see that there's no way to do that for a tuple. Now, as of Julia 1.0, named tuples are part of the base language. And what a named tuple allows us to do is to give tags or sort of internal variable names to the elements of our tuple so that we have a new way to perform a lookup inside a tuple. So that might look like this. Instead of declaring My Favorite Animals the way we did above, we might declare a new version of My Favorite Animals where the elements are still penguins, cats, and sugar gliders, the strings penguins, cats, and sugar gliders. But now we've assigned the variable bird to the first element, the variable mammal to the second element, and the variable marsupial to the third. So we declare this like so. And as before, we can use the number or the index of an element to look up what the value of that element is. So we can still say, what's the first element of my tuple? And we get that the answer is penguins, or the string penguins. But now we could also access, what is the bird variable inside My Favorite Animals? And when we do that, we see that we can get penguins that way as well. If we were to switch this out, we could say, My Favorite Animals dot mammal, for example. And now we're grabbing the element associated with the mammal variable, or the name mammal inside of our named tuple. Okay, so next up is dictionaries. We can create dictionaries in Julia using this capital DICT, this dict function constructor. We could call dict without feeding it any input argument. So I could just create a D, for example, where I say DICT, parentheses, and now I've created an empty dictionary. Alternatively, we can initialize a dictionary to have key value pairs. Now the syntax for doing that is shown in a general way up here where my mouse is keying over. So we'll put the key and then an arrow that we create from an equal sign and a right pointing arrowhead, and then the value to the right of that. And then we use commas to separate our key value pairs. My first example of doing this is creating the dictionary called My Phone Book. So here we have the key Jenny associated with the value, which is Jenny's number, and then the key, which is the string Ghostbusters associated with this phone number for Ghostbusters, included as a string. And having run this, my phone book exists, and we can perform a lookup, or we can see what the value associated with a given key is by throwing that key inside square brackets after the name of our dictionary. So if I say my phone book and then put the string Jenny inside square brackets, we get Jenny's number. And we can use very similar syntax to add additional entries or key value pairs to our existing dictionary. So if I put the value of a new key that I want to add to my dictionary inside square brackets after the name of my phone book, I can then put an equal sign after that and the value of the value that I want to associate with that key to the right of that. So here if we run this, we're adding Kramer and his phone number to my phone book. And if we run my phone book here, we can see that Kramer is successfully added. So we now have 3 entries rather than 2. Another way that we might update a dictionary is to delete existing contact info or delete existing key value pairs. And we can do that by using this pop bang function. We'll talk in a later notebook, actually in notebook 6, yes, in notebook 6 on functions, we'll talk about why some functions in Julia have an exclamation point in their names. But for now, we'll just say this is the function pop bang, which means pop followed by an exclamation point. Pop bang can be used to update dictionaries. And so if I call pop bang with dictionary as the dictionary name is my first input argument, and the key from the key value pair that I want to remove as the second input argument, and I run that, we're first off returning the value associated with the key value pair we're removing. And now if we look inside the dictionary itself, we see that Kramer has successfully been removed. Finally, I mentioned earlier that dictionaries are not ordered. That means that if I try to index into a dictionary with similar syntax to how I've indexed into a tuple, for example, I'm going to get an error. And the idea here is that because dictionaries aren't ordered, when you put a 1 inside square brackets after a dictionary name, Julia thinks you're looking for the value associated with the key 1. And there is no such key value pair that has 1 as a key inside the dictionary that we've created, so we just get a key error here. Now the final class of data structure that we'll talk about in this notebook is the array. And so we can create arrays in Julia by putting ordered collections of elements inside square brackets. And my first example of creating an array here is this one called My Friends. So one of the things that we see when we create an array is that we get a signature here that tells us first off how many elements are in the array we've created. So here we see there are 5 element array. And here we see what the type of the data structure we've created is. So this is telling us, if we read from the outside in, on the left we see the word array. This is an array that has dimensionality 1. So it's a 1D array. And what the value here says is what the type of the values included in this 1D array are. So this is telling us that this is an array of strings. Now, if we were to create another array called Fibonacci that has all integers, we see here that this is a 7-element array. And here we're saying this is again a 1D array that contains int 64s. Now there's no issue with creating arrays that have multiple types. So for example, here I'm creating this mixture array that has both integers and strings. And what we see here is that the type of the 1D array that's specified when we create this array mixture is the any type. Now we won't go into this in too much detail in this tutorial, but in Julia there is a type hierarchy, which I like to think of as I like to think of as a tree structure with the top of the tree being sort of where it all starts, the origin, rather than at the bottom. So in the way that I'm looking at my tree structure going down, at the very top is the any abstract type, and that encompasses all concrete types, all other maybe smaller abstract types in Julia. At the very bottom of the tree, we have the concrete types of Julia. So we have int64, float64, string, int32, float32, complex numbers. And sort of between that top of the tree and the bottom, we have some other abstract types, like number, for example, which encompasses all integers, all floating point numbers, but isn't a concrete type, and it's not as general as any. That was a lot of information. If you're not familiar with type hierarchies, don't worry about it all. You don't really need to know that for the purpose of this tutorial. All you need to know is that it's fine to create data structures with mixed types in them, and that often those will be interpreted as in any type data structure. So with that, we've just created a few different arrays that were all 1D. If we want to index into a 1D array like this, we can do that by throwing the number of the element we're interested in inside square brackets after the name of the array. So here we grab the third element of my friends, which is Barney. And if we want to update that element, we can do that by indexing into the array at the element that we want to change. And then to the right of that, we put the new value or the new element that we want to include at that position. So here we're changing Barney to Baby Bop. And I can prove to you that that happened by showing the values of my friends here. So we see that Baby Bop got successfully inserted in place of Barney. Okay, so two other ways that we might update an array are to use the push bang and the pop bang functions. So first off, push bang will add a new element to the end of an existing array. And so the array that we want to update is our first element, and the elements that we want to, or sorry, it's the first input argument rather. And the element that we want to add to that array is the second input argument. So here I'm saying push bang Fibonacci 21, and I'm adding this number 21 to the end of Fibonacci. Now if we want to remove 21, for example, or whatever is at the end of an existing array, we can use this pop bang function. So if I say pop bang Fibonacci, we return the number 21, and if we look at Fibonacci now, we'll see that Fibonacci terminates with the number 13. If I were to rerun these cells, we would keep popping off whatever's at the end. So here if we run, we see 13, and now if I rerun Fibonacci, we see that the last number now is 8. So these were all examples of 1D arrays of scalars. But we can also have arrays that contain other data structures as their elements, and furthermore, we can have multi-dimensional arrays. For example, in Julia, a 1D array is referred to as a vector, so you can use either of those names and be correct. And a 2D array is referred to as a matrix. So a matrix is an example of a higher dimensional array. Let's start by looking at arrays of arrays. So here I've created this array of arrays called favorites. And one of the things that we see when we create this array is that we want to read from the outside in to understand what type we've created. So this is still a 1D array. We see this is a 1 for our dimensionality there. But now the element type inside of our 1D array is other 1D arrays that contain strings. And notice that this only has 2 elements because it only has 2 subarrays. Now here, I'm creating this array called numbers. And what we see when we look at this signature here is that we have a 3-element array called numbers, where this is again a 1D array that contains, as its elements, 1D arrays that contain integers. So it's like a container with containers, with things inside those smaller containers. Now, lastly, we can talk about multidimensional arrays. One function that happens to generate multidimensional arrays for us is this rand function. So if I run rand here, we'll see what it's doing. Rand, by default, is using the input arguments that I pass to it, the integer input arguments that I pass to it, to determine what the dimensions of the array it should create will be. And it will, by default, populate the elements, or as the elements of the array that it's creating, with random numbers or pseudo-random numbers between 0 and 1. And so here, when I call rand on the integers 4 and 3, I'm generating a 4x3 random matrix. Now rand will take arbitrary numbers of input arguments. So if I call rand on 4, 3, and 2, we're getting a higher dimensional array, or in this case a 3-dimensional array, called, or not called anything, I haven't named it, but it is a 4x3x2 array now. And the last thing I want to say about arrays before we end this notebook is to be careful when you're trying to copy arrays. So we already talked about this array called Fibonacci. And let's say that I wanted to copy Fibonacci, and I think that I can do that by saying sum numbers equals Fibonacci. So if I do that, I have an array called sum numbers. If I index into sum numbers to try to change the first element to the number 404, we see that after doing that, if I look inside Fibonacci, Fibonacci has been updated. And the reason is that when I created the array some numbers, I wasn't actually creating a new array, I was just giving a second name to an existing array. So if I want to avoid this, if I want to actually create a new place in memory, a new data type or data structure, when I'm trying to copy an existing data structure, I want to do that by using the copy function or the deep copy function if I want to do this recursively to generate something that has a container that has many containers inside of it, for example. So I'll show you, this is me using the copy function, but first we want to restore Fibonacci to its original state. So now Fibonacci starts with the number 1 again. If I copy Fibonacci to create this array called some more numbers, I can now index into some more numbers, change its first element to 404, and I can convince you I did that by running some more numbers there. So there we see 404 got changed. But if we look inside Fibonacci, Fibonacci starts with the number 1 still.